The past isn't gone, not just emotionally, not just in our memories. In a very real sense, the past may still exist as physics. I know how that sounds. Like I'm about to argue for time travel, or some mystical everything is happening at once idea. But that's not what this is. This is about something much stricter and much stranger, whether the universe can ever truly delete information about what happened. Because in a minute, we're going to run into a problem that black holes create a problem so sharp that it forced physicists to rethink what it even means for something to be lost. And by the end, we'll come back to the title with a precise, testable feeling claim. The past might be preserved, even when it's completely out of reach. And out of reach is not the same thing as gone. But we have to earn that conclusion, slowly. When I say the past still exists, I do not mean we can visit it. I do not mean we can change it. I don't mean the universe stores a perfect playable recording of every moment like a cosmic hard drive. What I mean is narrower. It's about information. In physics, information doesn't mean secrets or knowledge or meaning. It means the detailed state of a system, which microscopic possibilities are still compatible with the way things are right now. And the key question is, does nature keep that information, even when it looks like it's been destroyed? Because if the universe is the kind of place where information can be truly erased, then the past really can be annihilated. Not philosophically, physically. But if the universe conserves information, then the past can be hidden, scrambled, and practically unrecoverable, while still, in principle, present in the structure of the world. This is the direction physicists like Leonard Susskind have argued for. Not that time is fake, but that the bookkeeping is deeper than our everyday experience suggests. So here's the thread we'll follow. First, why erasing is harder than it sounds. Then, why black holes look like the ultimate erasers. Then, why black hole physics unexpectedly points to surfaces, boundaries, and something called holography. And later this is important. We'll ask what it means for time itself to be emergent, not imaginary. Emergent, like temperature, real at our scale, not necessarily fundamental at the deepest scale. And somewhere in there is the answer to a question that should bother you. If the past is preserved, why does it feel so completely gone? Let's start with something ordinary, a cup of coffee cooling down. When you say, this coffee is hot, you're using a single word to summarize an enormous amount of microscopic detail. You are not tracking every molecule's motion. You're not listing the energy of each vibration, each collision, each fleeting arrangement. Yet temperature is not made up. It's real. You can measure it. You can predict what it will do, but temperature is a compressed description. It's what you get when you zoom out and ignore the fine print. Now here's a strange thought. What if your experience of time, the clean separation into past, present, and future, is also a kind of compression? Not wrong, just simplified. A user interface, because interfaces hide what you don't need. They're designed for action, not for full truth. Your phone shows you an icon, not the billions of transistor states underneath. A map shows you roads, not every blade of grass. And time, as we live it, might be the map, not the territory. Here's a quick, concrete experiment. Try to destroy a message, not just hide it. Destroy it so completely that even in principle, the universe could never reconstruct it. You could write a sentence on paper and burn it. The sentence is gone in the way that matters to you. But physically, what happened? The ink and paper turned into heat, smoke, ash, and light. The photons streamed outward, carrying away energy and microscopic correlations. The air molecules bounced and scattered, each collision imprinting something. In practice, you will never reverse that. You will never chase every photon and put them back where they came from. But that practical impossibility is not the same as fundamental erasure. A lot of modern physics quietly leans toward this idea. What we call lost is often just spread out and entangled and too complex to recover. And that difference destroyed versus scrambled is going to matter more than you think. Now, let's flip the intuition. Imagine the most violent, efficient shredder of information you can conceive. Not a fire, not a bomb, something that doesn't just break objects, it removes them from the shared world. That's what a black hole seems to be. A black hole has an event horizon, a boundary beyond which signals can't escape. If you fall past it, you can still see the universe outside, at least for a while, but the outside can't see you. So, if you throw a book into a black hole, the information in that book appears to vanish from our universe's accessible story, and for a long time, that looked like the end of it. The black hole keeps the secret forever. Then Hawking added the twist. Black holes aren't perfectly black. Quantum effects let them emit radiation. Over extremely long times they can evaporate. This raises a brutal question. If the black hole eventually disappears, what happens to the information about everything that fell in? If the outgoing radiation is perfectly thermal, perfectly random, carrying only a temperature, then the details of the book are not coming back. They're not hidden behind a horizon anymore. The black hole is gone. So where did the information go? If it truly disappears, then the universe has a delete function, and that would mean the past can be physically destroyed. This is the black hole information problem, and it's not a minor technical debate. It touches the core consistency of quantum mechanics, because in the standard quantum picture, the evolution of a closed system is reversible in principle. The present state contains, in a very exact way, the information needed to account for the past, not in a way humans can use, in a way the math demands. So if black holes delete information, something has to give. Either our understanding of black holes or our understanding of quantum theory, or both. For decades, physicists argued intensely about which option is less impossible. And if you want the headline version of where the field leaned, many came to believe information is not destroyed. It escapes, but in a form that is deeply scrambled. But why believe that, if the black hole looks like a perfect vault? Because black holes began to reveal something even stranger than the information problem. They seem to have entropy. Entropy is often described as disorder, but more carefully, it's about how many microscopic states fit the same macroscopic description. It's also tightly connected to how much information a system can effectively store. And black hole entropy follows a rule that feels almost like a message from the universe. It scales with the area of the event horizon, not the volume inside. That's not how ordinary matter works. If you build a bigger box, you can store more stuff in it, and the capacity grows with volume. But a black hole seems to say the maximum information is proportional to the surface. Let that sink in. It's as if the interior is not the main accounting ledger, the boundary is. If you want an intuitive image, imagine a sealed room where the total number of facts you can store is limited not by how large the room is, but by how many tiny tiles are on the walls. The interior could be enormous. The limit is still written on the surface. This is one of the stepping stones toward the holographic principle, the idea that a region of space might be fully describable by degrees of freedom living on its boundary. Holographic here doesn't mean the universe is a fake projection. It means the relationship between a volume and its boundary could be much tighter than classical intuition expects. In an optical hologram, a three-dimensional image is encoded in a two-dimensional pattern. The pattern doesn't look like the image until you shine light through it the right way. Likewise, in physics, a boundary description might not resemble the world it describes, yet still contain everything needed to reconstruct it. And suddenly, the phrase, "the past still exists," gets a new possible meaning. The past may be written into the present, but in a code we don't naturally read. Now, before we go further, an important honesty check. The holographic principle is strongly motivated and supported in certain settings, but applying it to our universe in full generality is still an active area of research. However, there is one place where holography is not just a vibe. It's a precise working equivalence, and it's the closest thing we have to a proof of concept that black holes don't delete information. It's called ADS/CFT. You don't need the letters, you only need the idea. In a special kind of hypothetical universe, one with a particular geometry, there are two different ways to describe the same physics. One description is a gravitational world, a higher dimensional bulk where black holes can exist. The other description is a quantum theory living on the boundary of that world, with no gravity at all. Two stories, one reality. Here's why that matters. The boundary theory evolves like a standard quantum system. And standard quantum systems don't have a fundamental delete key. Their evolution preserves information, so if the boundary theory preserves information, the bulk gravitational theory it's equivalent to must preserve information too, even when the bulk contains black holes that evaporate. That's a huge deal. It suggests that black hole evaporation is not a true erasure, just an extreme scrambling where the information comes out encoded in subtle correlations in the outgoing radiation. Now the limitation, our universe is not known to be exactly the kind of space used in this duality, so ADSA-CFT is not a final proof about our cosmos. But it is a demonstration that the impossible option gravity with black holes, and yet information preserved, is not only possible, it's mathematically consistent in a complete model. It's like discovering a working prototype. It doesn't guarantee your house already runs on that technology, but it changes what you think the laws allow. Now we can come back to the title question with sharper tools. If fundamental physics preserves information, then the past isn't something the universe discards. It's something the universe carries forward encoded in the present state, potentially across boundaries, correlations, and degrees of freedom we don't have direct access to. So why does the past feel gone? Because encoded is not the same as available. And because we live inside the system, not outside it. Let's talk about the arrow of time without turning this into a math lecture. In daily life, time feels directional because processes seem irreversible. A glass shatters and doesn't reassemble. Cream mixes into coffee and doesn't unmix. A message gets leaked and can't be unleaked. But notice what's really happening in these examples. Information is being dispersed into more and more microscopic degrees of freedom. When a glass shatters, the energy and motion get shared among countless molecules, vibrations, and tiny details. The world keeps track of what happened, but it keeps track in a way you can't practically reverse. This is where entropy enters, not as a mystical force, but as a measure of how many microscopic possibilities match what you can see. As entropy increases, the fine-grained details become harder to reconstruct from the coarse-grained view. And the past is, in a sense, the collection of those details. The more thoroughly they're spread out, the more the past becomes inaccessible while still existing as a pattern in the microstate. Here's a surprisingly simple way to think about it. The past survives as records. A footprint is a record. A fossil is a record. The rings in a tree are a record. Light traveling through space is a record. The structure of your brain right now is a record. Records are physical correlations in the present that point back to earlier events, and the universe is full of them. So full, in fact, that you can't stop the past from leaving traces unless you could somehow prevent interactions, prevent copying, prevent the world from correlating with itself. That's also why the past feels fixed. Not because it's sitting somewhere as a solid block you could visit, but because the present contains countless mutually consistent records that anchor a story. To change the past would mean changing all of those correlations at once across the environment, across light that already left, across particles that already scattered. Now pause. This is where some people jump to an extreme conclusion, so the future must already exist too, not so fast. Information preservation is not the same thing as predestination in a way we can exploit. Even if the underlying laws are deterministic or unitary, you can still have unpredictability for observers inside the system, because the information you need to forecast perfectly is distributed in degrees of freedom you don't control. And depending on how you interpret quantum mechanics, there are additional subtleties about what exactly counts as the state and who has access to it. So we should keep our claim disciplined. The past can be preserved as information without implying that the future is sitting there like a finished book. Now comes the deeper and more speculative step. If holographic ideas are pointing us toward a world where boundaries can encode volumes, and where gravity and space-time might be emergent descriptions of deeper information, then time itself may be part of the emergent story. Again, emergent does not mean fake, it means derived. A wave is not less real because it emerges from molecules. A hurricane is not imaginary because it emerges from air dynamics. Likewise, time might be real in the way we need it to be, consistent, measurable, causal, while still not being the deepest layer of description. In some modern research programs, space-time geometry is linked to patterns of quantum entanglement and information. That's not a single settled theory. It's a direction promising, unfinished, and still being tested. But the common theme is striking. What we call where and when may be ways of organizing information, not the other way around. If that's right, then the past existing could mean something like this. The universe's present state contains, in encoded form, the structure that came from earlier states, because the underlying dynamics never truly throw information away. So the past isn't stored in the museum behind glass. It's stored in the present, like a complex compression file that you don't have the password to open. Let's bring it back to black holes, because they're where this idea stops being just a mood and becomes a demand. If black holes evaporate and information is preserved, then what fell in must be recoverable in principle from what comes out, not as a readable story, but as correlations in the radiation. Which means the past event of throwing something in is still present in the future state of the universe. It never vanished. It was redistributed. And once you accept that, it becomes harder to say the past is simply gone in any absolute sense. Here are the implications stated carefully. First, gone often means inaccessible. A destroyed object is gone as an object, but its information may survive as dispersed physical correlations. Second, if information is fundamentally conserved, then the universe may carry an accounting of its own history even when every human scale trace is erased. Third, it reframes memory. Memory is not a magical bridge to a vanished world. It's a physical configuration in the present that is correlated with earlier events, another kind of record. And there's one more implication that's easy to miss. This is a statement about humility. Our experience of time is incredibly reliable at our scale, but it might not be the final word on what exists. It might be the interface that evolution gave us because it works, because it helps us act. So the past can exist as physics and still be unreachable. That's not a contradiction. It's the central idea. Now let's close the loop from the beginning. I promised we'd end with a clean version of the claim provocative, but not sloppy. Here it is. The universe may not erase history. It may only scramble it. Black holes are the reason we take that seriously, because they look like the perfect erasers until black hole entropy, horizon area, and holographic ideas suggest that the bookkeeping is deeper than classical intuition. ADS-AFT in a special setting shows that gravity and black holes can coexist with exact information preservation. That doesn't automatically prove our universe works the same way. But it makes information preservation a very natural expectation, not a desperate hope. And if that expectation is correct, then the past still exists, not as a place, not as a replay, but as structure in the present state of the world. Which brings us to a final, quiet point. Even if the past exists, you still live forward. You still make choices under uncertainty. You still learn, regret, celebrate, and forget. Emergent things matter. A map can guide you even if it's not the territory. Temperature can burn you even if it's not fundamental. Time can shape your life even if it's not the deepest layer of reality. So maybe the best way to say it is this. The past is not gone. It's just no longer yours to access. If you want more long-form documentaries like this, slow, conceptual, no equations, subscribe. And here's the question I'd love you to answer in the comments. If the past is preserved as information but practically unrecoverable, is that meaningfully different from being gone, or is that distinction the whole point?